I'm Tyler from UIUC, and today I'm going to present our paper, Who Watches the Watchers, on the reliability of Softwarizing cloud application management. I'm going to discuss the reliability issues of the management plane of the cloud applications, and then what can we do to prevent them. Those faulty management operations are causing the cloud applications to fail in production. Let me start this talk by showing you a real-world Postgres failure caused by a buggy operator. So suppose we have a Postgres cluster with 3 nodes, 1 primary and 2 standbys, managed by a Postgres operator. The standby 1 now is in a booting status due to a recent restart. Then the operator observed that the primary node crashed. And to restore the availability of the Postgres cluster, it needs to start the failover operation. The operator needs to pick a healthy standby and then choose it to be the next primary. However, the operator ignored the booting status of the standby 1 and picked it for the failover candidate. This caused the promotion to fail and leaving the Postgres in an unavailable state. Despite that, we actually have a healthy standby 2. Here, the operator which is managing the Postgres cluster violated the requirements for the failover operation and caused a full application outage. Faulty management operations are causing serious damage to the cloud applications. Many of the recent cloud incidents are reporting full application outage, significant performance degradation, or even sometimes security vulnerabilities. And those are not isolated incidents. Nowadays, those management operations are increasingly automated by software programs termed operators. Unlike the traditional one-off scripts or human-based operations, software operators are long-running system services that handle the full application lifecycle. The Postgres failover operation that we saw is just one of the operations issued by one of the Postgres operators. And today, on the de facto cloud platform like Kubernetes, almost all applications have operators to manage them, making the operator the de facto management pattern. Bugs in those operators have a magnified impact due to their nature of automation and widespread reuse. So why do the operators keep failing in production? Let's actually first look at what they actually have to do. Operators must interact with 4 external entities to manage the applications on top of the cloud platform. First, operator must interact with applications that they manage. They use the application API endpoints to monitor the internal states of the application and issue operations. They also manage directories and write configuration files. Concretely, for Postgres, the operator queries the get cluster endpoint to monitor its status and then posts to the failover endpoint to issue the failover operation. It also creates the data directory and also modifies the Postgres SQL configuration file. Second, operators manage the applications on top of the cloud platform. They rely on the cloud platform to provision the system resources required by the application. On Kubernetes, that means to create a pods to provision the system containers which runs the application processes, creating the cloud data volumes which get mounted to the application data directories and config maps which get mapped to the application configuration file. Third, operators sometimes have to share the cluster with other operators. When those co-located operators modify the same cluster resource, they can cause implicit dependency. For example, some custom network policy controller may inject some sidecar containers into a pod that are created by some other operators, and that can cause an interference. And finally, operators must interact with the user. They expose the declarative interface for the users to declare the desired state of the application. Those 4 interaction surfaces show a large space for the operators to go wrong. And to address the pressing reliability issues in the operators, in this paper, we make the following contributions. First, we present a study of 412 real-world operator failures that we collected from mature Kubernetes operators. And in this talk, we will see that the operator-to-application interaction is the largest, however, largely overlooked. To close this gap, we built Oat, which is a fully automatic testing tool focusing on the application interactions. Oat is a push-button tool for unmodified Kubernetes operators, and now it's part of the Akond project. Third, We applied OAT to 6 popular Kubernetes operators and have already found 86 new bugs in them. Many of them has been confirmed and fixed. So let's get started with the study first. To understand what are the reliability challenges in those cloud operators, we studied 412 real-world operator failures across 13 mature Kubernetes operators. Those operators manage server applications such as MySQL, Postgres, distributed systems such as Kafka and Zookeeper, and platform runtimes such as Knative. For each of the sampled failure, we analyzed their root cause and consequences. Most importantly, we found that majority of the operator failures are rooted in their interaction with the external entities instead of internal logical bugs. This shows the essential challenge of operator reliability. So let's zoom in into this interaction failure and see their distribution. We can see that the application interaction is the largest, consisting 42% of the interaction failures. There actually have been a lot of prior work in the community trying to improve the operator reliability, and they can be mapped to each of the interactions. For the platform interaction, we have testing frameworks like Sieve, verification frameworks like Anvil. For user interface, we have Akond and DCM, and for co-located operator, we have Kiwi and mesh test. However, application interaction, which is the largest category of the failures, have no prior work trying to address it or even merely understanding it. Our study aims to close this gap by understanding the failure patterns in the application interactions. We have found 4 recurring patterns in the application interaction failures, and the most prevalent pattern is the semantic violation, consisting 64%. This happens when the operators violate the semantic requirements of the application operations. The other 3 patterns are smaller. Observability problem happens when the operator fails to correctly observe the internal state of the application. Version incompatibility happens when the operators fail to handle the different behaviors across different application versions. And error handling when operators incorrectly handle the application errors. You can find the full details in all the patterns in the paper, and this talk is going to deep dive into the semantic violation. So precondition is actually one of the semantics frequently violated by the operators. Remember this Postgres operator failure that we saw at the start of this talk. In this case, the operator tried to promote a standby which is still in a booting phase and then caused a full application outage. This violated one of the preconditions for the failover operation, that the standby candidate needs to be in a ready state. What's interesting is that this actually is not a one-off mistake. Several months later after this failure happened, the same operator had another failover bug. And in this case, the operator picked a standby which is significantly lagging in its write-ahead log. When the standby 1 becomes the new primary, it overrides the data in the other standbys and created a silent data loss. After the failure, the developer then added another precondition to always check that the standby needs to have a minimum wall lag. And then again, a third failure happened. The operator promoted a node with async standby role while the entire Postgres cluster is running in a synchronous replication mode. Yet another precondition which is patched after the failure happened. We have seen 3 bugs in one operator for the same failover operation. Each fix revealed a precondition that are previously unknown to the operator developers. This shows an alarming gap between the operator and the managed applications interface. So precondition is just one of the semantic violations. We have 3 other patterns. Application configuration is the largest. They usually involve configuration dependencies across the nodes or modules of the managed applications. For example, the min.io operator failed to consistently update the membership list across the nodes when trying to scale up, and causing the nodes to be unable to join as a cluster. Ordering violation happen when multiple operations have ordering dependencies, and yet the operator failed to enforce them. For example, the MongoDB operator started the backup before the backup configuration is fully updated. This caused the backup to be started with the stale config. And finally, environment violation. They happen when the operator failed to correctly set up the execution environment for the application. We have seen cases in the Postgres operator where it creates the PG data directory to be too permissive and then violated the Postgres requirement. So let's step back from those concrete failure patterns and ask ourselves, why are the operators keep violating the application's management requirements? The deeper root cause is actually because those cloud applications are lacking a well-specified management interface. Their management requirements are ad hocly documented in their manual, source code, or even sometimes FAQ sections. So a lot of times they're not written down at all. Operator developers, who are oftentimes not application developers, have to reverse engineer those requirements. And a lot of those requirements are discovered the hard way in production after failures. So what can we do about it? In the long term, we need a real management interface which are formally specified. And the management interface needs to evolve along with application versions. But in the short term, we need a tool that can be readily applied to test the application interaction systematically and detect those bugs before they hit production. That's why we developed OAT. OAT is a fully automatic testing tool targeting the application interactions. It follows the state-centric operator testing approach proposed by our prior work Akond, published in SOSP 23. OAT models the operator's input space as a pair of the current application state and the state declaration, which declares the desired state of the application. The operators continuously reconcile the application from its current state to the desired state. Let's denote the state declaration as D and current state as S. OAT tests the operators by applying the new state declaration on top of the previous existing system state and chain them together as an operation sequence. One question is that, what is essentially missing from the current approach that prevents them from targeting the application interactions? And our study calls out two essential requirements. First, we found that 72% of the failures triggered by those state declarations need application-specific properties. That means that OAT needs to synthesize application-specific state declarations. Second, we found that 41% of the failures require faults on the application to be triggered. For example, the failover operation are only triggered if the primary crashes. That means that OAT needs to inject application-targeted faults. So let me give you a high-level overview of OAT's workflow. Given the application's interface specification, and in Kubernetes they are called CRDs, OAT synthesizes those application-specific declarations by mining the existing examples from the operator repo or by querying the large language model. And then OAT will have a pool of state declarations. Once we have those state declarations, OAT use them to execute the test campaign by applying them on top of the existing application state. Throughout the test campaign, OAT also makes sure that it injects faults to the applications, for example, application container crashes or network partition. And finally, OAT uses automatic oracles to flag those bugs when they happen. And then finally, it produces bug reports for the users. For evaluation, we applied OAT to 6 mature Kubernetes operators, and we have found 86 new bugs. This table shows the evaluation result, where each row shows the operators that we tested, and then each column shows the failure patterns from our study. If you look at the last row of this table, we can see that OAT has found bugs in every single interaction pattern from the study, and among them, the application operation semantic violation is the largest. OAT has found bugs in every single operator that it tested. In total, it found 86 new bugs with 0 false positive rate. To conclude, to improve and to understand and improve the reliability of cloud application operators, we conducted an empirical study on the real-world operator failures, and we found that operator-to-application interaction is the largest, however, most overlooked. We argue that manageability should be the first-class design principle when we design our systems. Nowadays, the cloud applications lack a well-specified management interface, which is causing the operator-to-application interaction to be so error-prone. And more importantly, as the AI agents are replacing those rule-based operators, those formal management interface become essential for the safety guardrails for the agents. As a near-term solution, we developed Oat, which is a practical testing tool that can be readily applied to unmodified Kubernetes operators, and it has already found 86 new bugs in 6 of them. So this concludes my talk, and I'm ready for questions.